Good day to you all. I am C.S. Srinivasarao, Associate Professor, Department of Computer Science, SVKP and Dr. K.S. Raju Arts and Science College, Penugonda. Welcome back to Graphs. We will discuss about the Euler path, Euler circuit and Hamilton path and Hamilton circuits in this class. What is Euler path? Euler path and Euler circuit. An Euler circuit in a graph G is a simple circuit. This is a Euler circuit is a simple circuit containing every edge of G. So it must contain every edge of G. That circuit must be, the Euler circuit must be a simple circuit and it containing every edge of G. Similarly, an Euler path in a G graph G is a simple path. The Euler path is a simple path and it contains every edge of G. So the simple, if it is simple path and it is every edge, it contains every edge. So then that is the Euler path, and Euler circuit is nothing but starting and ending point both are the same. Path is nothing but starting and ending are at different points. But in between from A to Z there is a path. So that is called path between the two vertices, and that path is the simple path and it contains every edge of a G. So don't omit any edge. So first you verify where these three are the graphs, whether this one is the Euler circuit or Euler path. Now for example, you take G1, this is the G1, G2, G3. G1 is there. What is the definition? Euler circuit, you must find the simple circuit and it contains the every edge of G. But one condition is there. Don't repeat the edge. Don't repeat the edge while traveling. So don't again go through that edge, right? Visit only one time. Each and every edge visit only one time. Now you find Euler circuit. Euler circuit means if you start at A, again you ended at A only. That is called circuit. Now you start at A and you visited like from A to B and B to E, E to, so you covered the A to B, you covered this edge, and from B to E you covered this edge, from E to D this covered this edge, from D to C this is you covered, from C to E this is covered, and E to A this covered. So you started at A and ended at also A. This is called Euler circuit. It covers all the edges. Hence this graph G is the Euler circuit. Whenever this is Euler circuit, the Euler path is existed, right? And second graph, you verify whether the Euler circuit or not, is there or not. For example, if you start at A, so you move from A to B and B to C, B to C, C to A and A to D and D to E and E to B. So, but you are not visited C to D, right? Or otherwise you can find another way. From A to D and D to E, E to B, B to C and C to D. So, and you neglect this. Like that you can verify that a Euler circuit are existed or not. Here there is no Euler circuit because you started at one point, you visit all edges without repeating and you come to the same vertex. That is called Euler circuit. But here whenever you start at A, you ended at A, but you are not visited all the edges. And there are two conditions. You must visit all the edges and without any repetition. That is the primary condition for Euler circuit. You must visit. You started at one point and ended at the same point. But you visited all edges without any repeating. Without repeating means again you visited the same vertex. For example, if you visited A to B, B to C, C to A to D and D to C, again D to B, B to E, E to B, B to A. You are visited so many times, the repeating, you repeated the edges. Hence that is not condition. So you should not repeat each and every edge. You visited each and every edge without any repetition. That is the condition for Euler circuit. So hence this graph is not Euler circuit, and there is no Euler path also, because you started it from A to B. For example, you find a path from A to B. So A to and you must visit all edges. That is the condition. Every edge, it contains a path, and it must contain every edge. So for example, A to D, D to C, C to B, you visited. This is the path, but you are not covered this particular these two cross edges and A to B edge. So but you find a path from A to D, D to C, C to B, but you are not covered A to B and here these cross edges. You must cover each and every edge without any repetition, right? So here there is no path and there is no circuit. There is no Euler. This is not Euler circuit. This is not Euler path. Similarly, you can verify whether the Euler circuit is not is there or not. Euler circuit means, again, you move from A to B, B to E, E to D, and D to C, C to A, but you are not visited here. See, you visited all vertices, A to B, B to E, E to D, D to C, and C to A. You are not visited these two edges. Similarly, you can find one A to D and D to E, D to E to B and B to A, but you are not visited these three edges. So hence there is no Euler circuit, but Euler path is existed. See, A to C, this is A to C, and C to D, and C to D, and D to E, D to E, and E to B, B to D. You visited the vertex again, but you are not repeating edges. B to D and D to A and A to B. You visited all edges. See that you started here. You go like A, C, D, E, B, D, A and B. A path from A to B. You visited all edges without any repetition. Hence, this is the Euler path. You started A, ended at B. That's why this is Euler path. This is not Euler circuit, right? For directed graphs. Now again you verify the directed graph. No Euler circuit, because A to B, there is, see, each and every vertex you must visit each and every edge. So A to B and there is no path here. A to D and D to C and C to B is there, but you are not reaching A. You are not reaching, you should not reach A, right? Here, because there is no incoming edge to the A. Hence, this is not circuit. This is not a circuit. This is not Euler circuit. Euler path is also not existed, because from A to B, for example, Euler path from A to B, one is A to D and D to C, C to B is there, but you are not visited this one. You are not passed this edge. So you neglect this edge. Hence, this is not Euler path. This is not Euler circuit. This is also not Euler path. Now here you see Euler circuit is there or not. So this is Euler circuit. A to G. See that it covers all edges or not while this path. A to Z and G to C, C to B, B to G. You can visit the vertex. G to E, E to D, D to F and F to A. You reached A. This is Euler circuit is existed. So obviously Euler path is there. And here you see that. Is there any Euler circuit? Here incoming edge is there, but A to B, B to A to this is A. A to B and B to C and C to D and D to B is there, but you are not using this particular in the particular path. So this edge is not there. Hence, this is not Euler circuit. Euler path is existed. See that C to A and A to B, from B to C and C to D and D to B. This is Euler path. You visited path from C to B. You visited all the edges without repetition. Hence, this is the Euler path. This is Euler path, but not Euler circuit, right? This is for directed graphs. There are two theorems. A connected multigraph with at least two vertices has an Euler circuit, so the graph must have the minimum 2 vertices. If and only if each and every vertices has an even degree. If each and every vertex has an even degree, then that is the Euler circuit. Now see, this is Euler circuit. This is Euler circuit. So degree of A is 2, degree of B is 2, degree of E is 4 even, degree of C is 2, that is also even, degree of D is. Each and every vertex degree is even, hence this is Euler circuit. Now here you see the degree of A is 3, odd, degree of C is odd, degree of B is odd, degree of D is 3, that is odd, hence this is not Euler circuit. Here degree of A is odd, hence that is not Euler circuit. That is the one way to find whether the circuit is Euler circuit or not. And one more condition is, it has Euler path but not Euler circuit. It has Euler path but not Euler circuit. If and only if it exactly 2 vertices of odd degree, exactly 2 vertices with odd degree. Now there is a one example. There is no Euler circuit and it has Euler path. It has Euler path. So see this. There is no Euler circuit and it has Euler path. Find out the odd degree vertices. How many odd degree vertices are there? This is the odd degree vertex. This is odd degree vertex. This is even degree vertex. This is even degree vertex. This is even degree vertex. Only 2 odd degree vertices. Hence, this is Euler path but not Euler circuit. Right? So these are the 2 theorems, 2 conditions whether you can verify the circuit is Euler circuit or not by using the degree of each and every vertex must be even. Then the circuit is Euler circuit. If the circuit is it has the Euler path but not Euler circuit, that means only exactly 2 vertices with odd degree. That is this one. And then Hamilton path and Hamilton circuits. The Hamilton path is nothing but a simple path in a graph that passes through each and every vertex exactly once. Here each and every vertex exactly once is called Hamilton path. And if it is Hamilton circuit, means it is a simple circuit, passes through every vertex exactly once. Here there is no repeating of vertices, whereas in Euler circuit there is no repeating of edges, whereas in Hamilton there is no repeating of vertices. Now you see the simple path from x0 to xn in the graph is a Hamilton path. Then the x0 to xn, there is a path from x0 to xn, and those 2 vertices are not the same. That means those 2 vertices are distinct vertices. Those 2 are distinct vertices, and it is simple circuit. The starting and ending point must be the same, x0 and x0. So this is a Hamilton circuit if it has the Hamilton path. Now see that Hamilton circuit is there. So here there is no each and every vertex exactly once. Every vertex exactly once. You started here, and you can move from A to B, B to C, C to D, D to E, and D to E to A. This is Hamilton circuit, right? This again you take. For example, you start from A to B, B to C, C to D, and D to. Again you move to B. You visited B again. So that's why this is not Hamilton circuit. Now for example, if you check the, you started A to B, B to G, G to E, E to F, you will not come back. If you come back again, you visited E. Hence this is not Euler Hamilton circuit. Hamilton path is existed here. It is a Hamilton circuit. Hamilton path is there. In this graph G2 there is no Hamilton circuit, but Hamilton path is there. A to B and B to C and C to D is the Hamilton path. Here there is no Hamilton path also, because you must visited all vertices A to B, and so that's why there is no Hamilton path, right? So the Hamilton path, these are the theorems. Degree 1 is Hamilton path. He has the graph G has a vertex with degree 1 is not Hamilton circuit. Hamilton circuit, whenever complete graph has a Hamilton circuit whenever n greater than or equal to 3. And Dirac theorems, Ohm's theorems are there. These 2 theorems are not. necessary conditions. These two are